Okay, so my presentation is going to be about a LedStrip Shader language that I wrote. So who am I? My name is Jereon Domburg, sprite_tm. I work for Espressive, hence me grabbing ESP32s everywhere. My personal website is spritesmonster.com. And you guys all know these, right? LED strips. It's very nice. You just dump 12 volt in them and they get a color. You can even get them more fancy where you have an RNG and a B thing. And depending on the voltage you put on there, they can go different colors. And then you have the really fancy ones, which have what Adafruit calls neopixels, which are individually addressable LEDs. These are great because if you don't know what effect you want, you just dump this in there and you can fix it in software.
Yes.
You don't like it, patch it. It's great.
Fix it in software.
So I actually want to have. Oh yeah, sorry. A bunch of pictures are upside down. I have no idea. Anyway, I love them. This is upside down. This is my kid's playhouse. I upgraded it a bit with LED strips, and she has a button she can press for different effects. It's awesome. These are also neopixels, but they are slightly modified 1 watt RGB LEDs in there. But I added effectively one of the neopixel chips, the controllers, the clones of the one that you could put in parallel. And there's 2 of those chips in parallel in each of the lights. And this entire string of LEDs you can control more or less like a neopixel strip because there's 2 chips in each thing, and the channels aren't paralleled up very logical. You do need some software modifications in order to make it work. But if you have the driver, these are neopixels. Same thing again, 90 degrees rotated. Our bed also has a night light, which also is one of those strips because I had them anyway, and they're cool. What do I use to drive them? Well, there's a few options. I use something myself, but you don't need to. You have WLED, which is a great, I think, Arduino framework, which also runs on ESP32s. You can have lots of different effects, etc. You also have Night Driver, which is an alternative thing, also Arduino-based, if I recall correctly. But the issue I have with those is the effect design loop. If I just want to have a generic effect, like a U, like something that scrolls over it or different patterns or whatever, it's not that bad because I can kind of sort of use my brain to figure out what it needs to look like. I can open up the code. I can write a little bit of code that does the pattern. And then I need to recompile the project. I need to plug in my ESP32 or with OTA or whatever. I need to compile it. I need to flash it. I need to re-plug it into the strip if it's not there. And then I can look at the effect. And if it's okay, then you know I'm happy. But, well, you saw my use cases. I have a bunch of lights in plants. The plants are all differently. Maybe I want to have the big plants lit up differently than the small plants. I could do that using this, but that would cost me a lot of work purely in, oh no, that needs to be a little bit more red. Unplug the thing, plug it in, edit the thing, compile it, upload it, replug it, unplug it there. No, now it's too red. Unplug it. Well, you get the point. So maybe there's a better way. What if I do the editing not in the main CPU language like C or C++ or Arduino or whatever, but what if I use an on-device virtual machine that I write my effects for? That way I take out a whole bunch of steps because rather than recompile the entire firmware, I only need to compile my little shader effect and then send it to the processor. And that effect is tiny because it doesn't need the driver, it doesn't need the operating system, it does nothing. So the loop is a lot faster. And because I don't need to reflash it, I can do this over Wi-Fi if needed. So it's a great idea. It's also not mine. This is Ben Henke. He is a guy, I spoke to him years ago at one of the Hackaday Supercons, and he actually talked to me about what he made. And what he made is this Pixel Blaze, which is a Wi-Fi LED controller, which more or less works like that. You plug it into an LED strip and you connect it to Wi-Fi. You get a nice IDE. You can edit your code. and it immediately shows that. And that's great. The only issue is that he sells these. Like, this is the only way in which you can get pixel blaze, by going to a shop and buying a module, which, don't get me wrong, I have absolutely nothing against people working hard for it and then selling it and not wanting to open source. That is their choice. I don't like, the guy worked hard on it. He deserves a bit of money. But the issue I have with it, if I want to use it, I can't do things on it. I want to connect this to Home Assistant. I can't. At least maybe I can, but I need to have some sort of translation layer. Yeah. I can't have an extension to the language. Who knows? Maybe I want to, grab the current weather in Singapore and then make everything blue if there's a thunderstorm going on or whatever. I can't really easily do that. Obscure LED protocols. This thing works great if you have a standard LED strip. I told you about my garden light. That thing is not a standard LED strip. If you control it like a standard LED strip, you're not going to have a fun time. But again, I can't change it because it's closed source. So let's just build my own. Yes. Okay. So first of all, the language itself. The language itself kind of looks like this. It is inspired by C and JavaScript and designed in such a way that I'll be hated both by C lovers as well as JavaScript lovers. It is simple. It doesn't have any crap. You don't need heap allocation to just write an LED shader. Floating points, we also don't do that because most of the chips I want to do that on don't really have floating points. You've got something else. Lambdas and objects and etc. You don't use that anyway. And if you did use that, you don't use them now because the language doesn't support them. It also has a base type. That is one thing I did need to thank the Pixel Blaze guy for. The base type is a 16.16-bit floating point. It means that it's a thing that goes from plus 32K to minus 32K, and it has a precision of 164K. So it kind of sort of works like floating point if you stay within those boundaries, but because the hardware can act like it's a 32-bit integer, and that's native to the hardware, it should be really fast. So plan is I need to make a compiler, easy peasy, Friday afternoon. I need to have I need to design the actual virtual machine, and I need to implement the virtual machine interpreter, so to say. So I decided to go for C and Emscripten. C is, you guys know C. Emscripten is a thing that takes C and converts it to WebAssembly, which means that you can run it in a browser, and that is very useful. So first of all, if you write a C compiler, there's a bunch of standard things you need to do, and one of them is tokenizing and parsing. There's a few options for it. You can do that yourself if you feel really horrible and want to have a bad time. Luckily, it's already solved. If you do it the correct way, you go for Antler, which is a great modern thing that's written in Java, seemingly really great. Or you just use tools that exist for 40 years already, and you go for Python and Flex. So I decided on the last thing. It's actually not that bad. It's because it's been around for a long time. The documentation is stable. You don't have to worry about versions because all versions are ancient. So there's stuff out there. Okay. So how does that work? Say we have this statement. First of all, we need to tokenize it. Effectively, there's a bunch of rules that effectively say, oh, if you encounter this, that is this token. And that is done. So var, for instance, is 3 letters. I don't want to do a string match all the time. So that just becomes one token, one integer. If it's actually a number, the thing does a little bit more. You can see here that it actually interprets that number and stores it because, I'm at it anyway. I might as well do it. So if you tokenize it, this is more or less what it looks like. You can see that it took the var, and that is a variable token. Variables themselves, the tokenizer doesn't quite know what to do with it, so it's a string. It's fine. Equals, plus, minus, etc. It does recognize the numbers. It recognizes the semicolon. It recognizes. You throw it into a parser, Bison in this case. So you have a bunch of rules that effectively tell Bison what the language looks like. I don't really have a great example for this, but in this particular case, you can see that the definition of a var is the word var and then something else. And that something else is defined as something else again. And it uses that in order to look at all the tokens and to figure out what the relationships are, more or less. So what happens effectively is you see a bit of code underneath here. Underneath here, I'll also help the Zoom people, that effectively get the left side of whatever's there and the right side of whatever's there. And your code can do something with it. It can, for instance, pack that into some sort of object. And if the entire thing is the right side or the left side of something, then the next call for the bigger function will again call something like this. But in that case, the right side is the output of the thing that you just made. I hope that's clear. So what I do is I make this into an abstract syntax tree, which is a great idea. I have no idea if I implemented it correctly. I've heard it once, then I read the Wikipedia page, then I was like, ah, yeah, I can do this. So if potentially computer scientist people will cringe at that. But an abstract syntax tree for the function that I called kind of looks like this if I am done parsing it. So you can see that there's a declaration, that's the var a, I declare the a variable. And then there's the assignment, what it should be. In this case, it needs to be 2 times b plus 1. And that all needs to be stashed in the a variable. I hope you can see that how this tree effectively does what that function just wrote out. So once Bison is done with everything, then this is what I get out of it. So an abstract syntax tree. Now, this is not code yet. This is nice, but you need to have a bunch of classes on there. So one of those classes, for instance, is that you all these lines are effectively objects in memory. You can annotate them. You can put a little bit more information in there. So, for instance, there's a reference to an a variable here. And what I can do is say, oh, yeah, this a variable is declared here. So if later on I need to output my code, I can put that a variable somewhere in memory. And then everywhere that references it has a reference to the node that knows where the variable is in memory. So it makes it very easy for me to make it into code and to fix up all the relationships. So there are a bunch of more steps. And if that is done, we go and create the code. So the pink bits here are the actual code nodes that are generated. And I just stash them in the same abstract syntax tree. I worked hard on it. It can do everything, right? So you can see that my code went over the tree and added a bunch of instructions. So this is the load effective address of the variable a here. Then it pushes 1 to the stack and it pushes 2 to the stack. It loads the variable b. And then this is a stack-based machine, by the way. Everything that happens is because stuff gets pushed on the stack and popped from the stack. So the mul instruction pops 2 things from the stack and multiplies them and pushes the result on the stack. So it multiplies 2 and b and pushes that on the stack. Then you have add. All the way in the beginning, I push the 1 and it takes the result of the multiplication and adds those 2 together. And then finally, the last thing on the stack is the address of the a variable. And the store instruction just stores, pops the value of the stack and stores it there. So we now have like machine code for the virtual machine that can do the thing that I just said. So that is more or less how the compiler works. This is the code in the end. So these are effectively the virtual machine doesn't really have an assembler, but you could put this in an imaginary assembler and get proper code. Okay, so how is this implemented? Well, everything is implemented in an ESP32. I work for Espressive, they're free. So ESP32 has a bunch of HTML and JavaScript, and that also includes the mscriptonized compiler, more or less. So if I connect my laptop to it, my browser loads up that HTML, that JavaScript, that WebAssembly, and what I get is an IDE, just a screen where I can enter my code. So the thing also has a compiler, and it is very eager in compiling. If I don't touch my keyboard for 2 seconds, then it'll recompile. Like, you know, take your compile things and smoke that. If the compiler is done, you get a binary, and that can be run in a virtual machine. And it actually gets run in 2 virtual machines. One of them is in the browser. You have a virtual LED strip that you can, you know, check immediately. The other thing is it makes error finding a lot easier. If your program crashes immediately, if that's in the browser, I can just do a callback to the IDE and say, hey, this statement here crashed. And that makes finding an error very easy. You just get like one of those wiggly lines, you know, you made a spelling mistake here. It also sends it to the ESP32, and the ESP32 also has the same virtual machine, but it has actual physical LEDs that it can control. Okay, so this is what it looks like. Effectively, you know, you just have a browser and you can code, and under here is the virtual LED screen. And I'll do a little live demo if
you could figure out.
if I can get to the screen. There's a page up. Yeah, ha, I can use the keyboard. Keyboard to the rescue. Okay, so I'm just going to edit something. So I have the U switcher here. Ooh. And I can edit it as well. And this is more or less what it looks like. This is the function. Everything starts at the main that just registers an LED callback that gets called for each LED. That LED callback uses the time and the position in order to calculate something. And in this case, it's just a bunch of signs, one for each color. So say I don't want to have white anymore, then just comment it out. And 2 seconds later, the white is gone. Say I want to have it want to be very bright red, then I just edit it like this, and 2 seconds later the red is very bright. And you can see it change both in the thing as well as in the strip underneath. So I've got a bit more complicated thing that I'm not going to explain entirely, but it kind of shows what the thing can do. So this ESP32 is actually configured for like a gazillion LEDs, so it's a bit slow to run this. But this is what it does. The language actually supports structures, so you can group your data. And what the function does, it updates. In this case, you have a structure for each particle that goes over the thing. And there's a function that gets run once per frame that updates it according to the speed and the color, etc. And then the actual LED thing just checks for each LED if there's a particle nearby, and if so, then it lights it up in the proper color. But yeah, as you can see, syntax highlighting works, everything. Again, I can make a typo, and you can also see that it puts a green scribbly about in the right way. Error handling is not entirely correct, but you can see that, you know, it doesn't get it, and the error is here. So that's more or less the thing. Then I go back to.
Thank you.
Okay, so a bit about the state of the project. The project is, I've written it in such a way that it's portable. So it comes with an ESP32 project that you can just dump into a random ESP32 and you get effectively what's running on this LED strip. You can also take the WebAssembly in HTML and just dump it on a web server. In that case, obviously, you don't have a real LED strip, but you could use, for instance, the binaries in order to upload them to a server and control a whole heap of LED strips at the same time or whatever. In theory, you could compile this and run this on a Raspberry Pi as well if you wanted to. I've tried to make it very portable, and I've tried to make it reusable from like only the virtual machine to the entire project. That also means it's hardware agnostic. As I said, Raspberry Pi can probably run this as well. You just need to recompile it for Linux and hook it up to a different web server. It is open both in the sense that this is open source. I don't remember what license I slammed on this, if anything, but it's probably going to be MIT or probably Beerware. I like Beerware. But it's also open in that the language itself is extendable. You saw that there already were a bunch of functions defined, like rand and sin, etc. It is pretty easy to link in another C file that defines another function. So if you want to have a function that, well, the example I mentioned before, that grabs the weather from somewhere and returns if it's sunny or not, then you can easily write that. So the downside, this is I wrote somewhat alpha. That is an understatement. It's very alpha. So I don't know exactly what direction I need to go with this. I do really want to have this be something that other people use as well. I mean, I can throw this at my own ESP32s and then, you know, I just write my own code and chuck it in a few things and that's fine. But I kind of want other people to take this and run with it as well. But I don't know exactly what direction I need to take this in order for other people to be happy with it. And that also hooks into the last thing. It needs more users and developers because at the moment we've got just me. So I kind of, you know, if you're interested in this and want to play with it even, then go ahead. Okay, that's the end. Thanks for listening. The repository for the thing is up here. LSSL is the project of the name. SpriteTM is my hub and is my GitHub. If I can go here, code is here. There's also a demo if you wanna look at it. That's here. That effectively sends you to the web server only thing. So you can just load this anywhere in a web browser and you can play with it. It loads, it does the thing, it shows you the virtual LED screen, etc. Okay. Yeah, so the thing about this presentation is I've written this while I was, you know, knee deep in the project, and the issue is that a whole bunch of things that might be unclear seem perfectly clear to me, so clear that that it's not worth explaining. I know that that can be a problem. So if you have any question at all, don't feel stupid. I might just have overlooked something like super complicated. So any questions? Yeah.
There is one that I have to make because I think it's expected of me. So of course, there is a thing called micro-HS, which is a Haskell runtime that seems to be run on very small, very resource constrained devices. Do you have how much RAM does that have?
About half a meg.
Oh, okay, so easily. So that's right. But the reason I'm doing that is because I think it would actually be quite a nice use case for this because like, programming this as a function of the position is actually quite, and the time and the state that you know, is actually a very natural way, I think. And the more serious one, because you know, I don't really expect you to drop everything and just go to Haskell, but I think the more serious one is, have you thought about using a force for this? Because this is pretty much the use case for force, right?
Whom of you have ever written a non-trivial program in Haskell? Who of you have ever written a non-trivial program in for?
That's probably this
Whom of you have ever written a non-trivial program in C? Whom of you have ever written a non-trivial program in JavaScript?
Yeah, probably.
Okay, that's less. Yeah, well, I mean, you know, and yeah, my point. To be fair, they're
in a JavaScript program and not hate it. Wrong either for that one.
Hey, I told you before, I was going for the crowd to hate this, so no.
You just say you put Haskell, and the Haskell people also hate you, so you get more hate.
So the thing is, I've actually looked at other things because my initial thing was so the Pixel Blaze thing is a subset of JavaScript, but it's a narrow subset of JavaScript, as in it doesn't do things differently than JavaScript. It just has less features than JavaScript. So my first idea was, oh, I'll just take any random JavaScript interpreter. You know, you've got V8, you've got micro.js, you've got a whole bunch, and I'll just throw that at it. And then I kind of got like, you know, you have a whole bunch of functionality that you don't need. I don't need, strings even. I don't need strings. I don't need objects. I don't need garbage collection. I don't need any of that. I don't even need floating points. And the integers that they give me are a pain in the ass because the 16.16 point is way more feasible for that. So most of the interpreters, virtual machines, compilers that I found were just not aligned with what I wanted. And that's the reason why I decided to go and build my own.
Even something like Lua. Even something like Lua.
Even something like Lua is fairly, I mean, Lua is more or less a systems programming language, so there's a whole bunch of features. And I think it also has objects, and as such also needs to do garbage collection. I'm not sure, I'm not a Lua user. But like, you don't want your LED strip to hang for a second because it needs to do garbage collection. So yeah, like there's a whole bunch of things, like even MicroPython you could write this in, but it's all not there's a mismatch with what I want in an LedStrip shader language. Okay, more questions?
Understanding what exactly
Sure.
so what is something for people to program the LSSL is that I think so comparing this with, for example, you know, if you use some the like for example some libraries you know like the rainbow library or like some flashing library. So how easy or difficult to use to let's say make a rainbow using what we have created.
Okay, so I think I showed you the uCycler thing. If I can get there. Oh, wow. Automatically.
Didn't think you could do.
It's an extra feature. Either that or a bug. So I'm not sure if this counts as a rainbow or if this was what you wanted.
Oh, okay.
So like a rainbow is this, and I'll leave it to you if that's hard or easy.
Would it be possible to adapt this to what we make a series state?
Yeah, you could. That's actually something that the Pixel Blaze guy did. He has functions that, as a position, take a 2D or even a 3D argument. So you can effectively use the position in space in order to calculate your effects.
But I mean, that's tricky if you work from this because you can pre-compose your function with some.
I agree. It's fairly trivial to add. You would need to create a driver that drives an LED matrix in what shape, way, or form you want it, and then you would need to add a function that does the 2D mapping rather than the 1D. But that's just copy paste more or less.
I missed a bit of thought earlier. You said you wanted to plug in for v8.7. How are you doing that?
Sorry again? You said?
You talked about you want to extend it for v8.7.
Yeah. So I'm not sure yet. I have like another project of mine is or a project that's more something that I wrote for myself with code quality to match. So I'm not sure if I'll ever dare to release that. Like the idea is that you can use Home Assistant in order to set the brightness and select the program, more or less. So you would still need to have to go to the web server in order to edit the effect, but as soon as you're done with the effect, you can just select it from Home Assistant, something like that.
So another way you could do it is to have some generic object that is passed all your effects, and then the contents of that object are what is changeable using code automation. So you can have the parameters separate from the code.
There's options like that as well. That is the bit where I said that I'm not sure what direction to go in. I don't know what the easiest is yet. So for instance, I already made a bunch of choices that I'm not sure about. So the way I implemented this, for instance, is that the entry point is a main function, and then you need to register callbacks. But you could make the point that, you know, why would you do that? Just have a function in the program that's called set LED that just gets called every time an LED is done. There's a whole bunch of architecture decisions like that I'm not particularly sure of, and at the moment I'm just doing stuff. I picked the main function, first of all, because registering a callback is nice, but also it is very easy for me to only export one function called main from the binary. If I need to export more functions, my code will get more complicated, and I'm too lazy to do that while this works. So
I'm going to tempted to use the Arduino style setup and loop. But it's two, that's always the same two. It's always exactly the same.
yeah, it's also an option. I kind of made this into a function because the reference to a shader language. Shader languages also more or less work in such a way that you have callbacks. The reason they do that is so every single pixel or tile or triangle or whatever, what have you, can be run on one of the different GPU cores. And I am like, technically I could use the 2 cores on the ESP32 to split up calculations, but
One string.
for one string, yes.
It's too big.
It's a very, very large string. I don't know. Again, it's a choice that I made that is absolutely debatable, 100%. I don't know if it's the right choice. It is a right choice in that it works. So I'm going to stick to it unless someone comes up with a counter argument. Okay.
Thank you.